My name is Gunter Ollmann. I'm going to be talking about DGAs, domain generation algorithms based on malware, and how they operate, how they can be optimized, how the bad guys are using them, and how the good guys can detect them. The obligatory about me, so I'm a CTO stroke VP research for Dambala based in America. I'm on various advisory boards. Formerly IBM Chief Security Strategist, came to IBM via acquisition. I ran X-Force R&D for Internet Security Systems, and before that I was based in the UK, London, for NGS Software. I used to be running their professional services. So much of the stuff I'm going to talk about, I spent quite a bit of this morning removing a lot of material that was very mathematical. I just wanted to list a few of the folks that have been working in this particular area. Some of the things I'm going to discuss are new innovations, new ways of analyzing this particular class of threat. And as you'll see, it's a very complex threat, and it's using a new different type of technology. And one way of looking at this is, if you like, the science of security. There's a lot of this work here is done by Georgia Tech University, and a lot of these folks here have been working in the area for quite some time, mostly in machine learning and learning systems. So generally, the agenda is basically going to be, DGAs, what are they? Why are they important? What do they do? How do they work? How do you detect them? How are the bad guys using them? And what will the bad guys do next? So first off, when I talk about DGAs or domain generation algorithms, what are they? So DGAs are a type of domain fluxing. And so what's really happening here is that there will be an algorithm behind the scenes that will, given a particular seed, maybe a date timestamp, will then be creating domain names on the fly that say a piece of malware or a server infrastructure are going to try to taste to see whether there's an answering machine at the other side. So domain fluxing is one of the older terms for it. It's typically used today as a means for advanced malware to locate its command and control servers around the internet, as well as the upload servers. So if you have a piece of malware that's stealing credentials, it's got to upload it somewhere else, so it needs to find that final destination. So where are DGAs actually employed? So on the client side, when we look at the malware fronts, you talk about droppers. So they're used to locate the download store. So I have a small agent that's been distributed as part of a drive-by downloads through some exploit, for example. And it's a very small agent. It now needs to reach back out to a server to pull down the actual malware download itself. Or inside the malware, where it has to, once the malware is loaded and stored on a particular host, it needs to find the location where it's going to drop the stolen credentials. Or within the bot agent as it's trying to hunt and connect to its command and control server. We also see it happening over the last year and a half now, more coming on the server side. So where the bad guys have been extra paranoid about including the algorithm inside the malware that can be reverse engineered, so they put it on the server and get the server to generate one-off domain names for all of the malware elements. Another element is actually building it into the DNS services themselves. So the DNS servers are actually using CNAMEs using dynamically generated CNAMEs to then point to the real DNS servers. When you see that, often it's basically fall into an area what we call triple flux. So you'll have the fast flux, double flux, and now the triple flux, where you're having the IP address of the destination changing, you have the IP address of the DNS server changing, and then you have the domain name changing that's pointing to the DNS recursives. So what is the goal of a DGA? So primarily what we see in the most advanced malware that's out there, in particular things like the banking trojans and type of things, they're therefore hiding the location of the command and control servers. The reason for that is to provide extra resiliency against takedown. So instead of having a single domain name pointing to my command and control server somewhere, I can automatically change that destination of the DNS side constantly. Okay. which means that it's much harder for the good guys to be able to locate the command and control server and actually take it down, or to try to take ownership of the domain name that's pointing that way. It's also designed to bypass filtering technologies. Okay, so you can take something like an older style DGA malware like config.c. So config.c had an algorithm that would try 50,000 possible domain name candidates using the algorithm. The malware would randomly sample 500 of those, and hopefully of those 500, one of them will be a live command and control server. If you're operating a filtering technology, you'd want to add the entire list of all the possible DNS candidates into your filter, and you'd have a list of 50,000, a blacklist of about 50,000 for one piece of malware. Okay. But today there are many, many strains of this malware that are out there that have their own DGAs and their own algorithms there. It's also a way of avoiding signature-based detection systems. But I think one of the coolest things, if you like, on the DGA side is really this long cycle of bot recovery. So I can distribute a piece of malware, let it go infecting and just worming its way or building up an infection base. And I don't actually need a command and control server until I actually want to use it. So I can distribute it, and then a year later, I can then set up my command and control server, and I can gain control of that. What we also see it as DGA is now being added as a functionality into most of the malware construction kits as a fallback plan for CNC discovery. So why do DGAs work? They're basically generating more domain names than is practical to actually detect or block. From a takedown perspective, it's very, very difficult because most of these domain names are generated on the fly. But more importantly, as the bad guy, I can just select one of those domain names for that particular algorithm and decide to register it, half an hour before I know the algorithm is actually going to hit it from the malware side. Set up my server, set up my DNS servers, point to my actual IP-based command and control server, allow all the malware to connect for a couple of hours as the algorithm changes, and then disconnect from the internet. And so from a law enforcement perspective, it makes it incredibly difficult. In fact, basically makes it impossible for law enforcement to be able to take down these types of servers in time. So the fact that the server only has to exist for a very short amount of time provides a lot of benefits to the bad guys. Another key thing there is that the algorithm itself is probably not good enough for good guys to be able to defeat this. So even if I have a piece of malware and I reverse engineer it to get the algorithm is typically seed-based, and so unless I have a copy of that particular seed, then knowing the algorithm isn't actually going to help me predict what's going on. Now, when we look at malware families that use these technologies, I sort of break them down into two generations: the first generation and the second generation. The first generation, things like Conficker, Boback, Cinnawall, Kraken, Shrewsbury, these are all malware that are basically famous because they had DGAs. Okay, so they were interesting enough to be named something different because, frankly, that they had DGAs. Now when we look at the second generation of DGA-based malware, these pieces of malware aren't famous for their DGA. They just have DGA as a functionality inside their software. Okay, and so what we often find is that for things like the new TDL5, I guess if you want to call it, has a static list of a configuration file with static domain names that it uses for command and control. If it can't locate those, or if there is any blocking of those command and control domain names, it switches over to peer-to-peer and searches the peer-to-peer to look for a new configuration file. If it can't connect to peer-to-peer or it doesn't receive a valid configuration file, it then flicks over to DGA mode to then start hunting for its command and control servers. So, the most famous ones that you'll see, today will be the TDL, Zeus, in particular, Morifit variants, and Bankpatch has been getting an awful lot of publicity over the last year in this zone. Now, what do these sorts of things look like? What do these DGA domain names look like? Here is a small sampling of config.c. Config.c was interesting in that it tried 50,000 possible domains, randomly sampled 500. If you look at this sort of structure, they preferred .net.com as the top level domain, and then it was lowercase regular characters, no extended character set, and a random size generator. Okay. Other ones that you'll see floating around, so these are two versions of Morifet. So Morifet A, Morifet B. And so you sort of see, Morifet A had a fixed length 2LD and cycled through the org and info domains. Meanwhile, Morifet 2 or B2 had a slightly different sort of algorithm. But they all sort of look a little bit different, and if you understand the malware and you get the DGA to run, you can build up these types of profiles of what the domain names that they're actually trying to connect to, and there is generally a structure from these. And if you really want to try, you can sort of think about maybe developing your own algorithm for understanding this. You could also try to develop a signature for detecting these particular domain names. Put that in context though, let's have a look at something that should be fairly easy. So Morifet A, here we're talking about a domain name that's that long. It's pretty much always that long, and it only cycles through a number of 2LDs, org, info, and biz, and then cycles through these continuously. So when I looked at the Morifet V1, so having looked through, I looked at our passive DNS database, so all the DNS record sets or RR record sets for just 1 week. And use a nice simple regex statement, and basically very simple, something between 36 and 40 characters long, ending in biz.org.info.net. For that particular 1 week on our passive DNS, there were a little over 31,000 2LDs of that meeting that particular criteria. Having a closer look, only 967 of them were actually associated with the malware. All the rest were basically legitimate domain names. So this is a problem with even something that should be fairly simple. There's an awful lot of legitimate use of garbage domains out there. Okay. So what about the reality behind DGAs? I guess part to understand really is that you have an algorithm that's given a particular seed, a particular timestamp, an epoch of time, can generate a number of candidate domain names, if you like, this big blue circle. The malware itself doesn't need to try every single one. In fact, most of the malware will only taste a smaller sample of those. So here we have the red spot representing the number of potential domain names that the algorithm generates, but these are the ones that the malware is actually going to try to connect to. And then, if you like, a live command and control server sort of floating around on the internet. Now, there are some strengths and weaknesses in this approach. Now, if I'm the bad guy and I have an algorithm that gives me a very large pool of domain names, of candidate domain names, then the percentage of those domain names that can be preemptively blocked. So the good guys who reverse engineered the software or have a copy of the algorithm, they want to create blacklists or something like that, or signatures and roll them out somewhere. If I have a fairly large algorithm or large candidate base, the probability that they'll be able to block them all is pretty small. If I reduce the scope and have a smaller candidate base, then it's obviously a lot easier to preemptively block or take down these types of domains. The reverse of this, though, is that I may have a big candidate base, however, depending on what I'm actually tasting. So the more I taste of that candidate database or candidate domain names, the higher probability that my piece of malware is actually going to be able to successfully find, locate, and connect to that command and control server, and the reverse is so if that sampling is too small. So if you like, there's a sweet spot, a Goldilocks zone for your DGA construction. Okay. Now what we find is that you'll have tens of thousands, hundreds of thousands of bot-infected victims or pieces of malware that are floating around there. They have this algorithm and they'll be sampling or tasting some of the domain candidates from the algorithm. And at any one particular time, there may only be 1 or 2 or 3 command and control servers actually live. So physical servers, IP-based servers somewhere on the internet. And however, the DNS infrastructure is pointing to these particular domain names at a particular date and time. And those domain names may have only been registered a few minutes ago, a few hours ago. And so what we see is that you have this algorithm that's being used to locate where the potential command and control servers are. Meanwhile, the physical command and control servers are IP-based somewhere on the internet, and basically what you find is that over time this candidate pool is shifting Okay, and the command and control servers themselves are also changing. Okay, so what the bad guys are doing, they're changing, they have an algorithm that's changing, they're sampling only some of the domain names, they're registering only a few of those domain names, and then they're also physically shifting the IP addresses of the servers, and then over time also those servers, the physical servers will have different domain names pointing to them. Okay. So this just gives the bad guys tremendous resilience and the ability to flux their command and control infrastructure on many sort of levels. What this means, though, is that from a law enforcement side, or the ability to take down these types of domains or locate the infrastructure, it's almost impossible. Many of the operators that I track today, especially the ones that focus more on the frauds and banking fraud side, what you'll find is that their preferred IP hosting are going to be in things like Better Business Bureau or RBN or BizCN or some of these other hosting facilities where it's basically impossible for anyone to take down or get access to these servers. Okay. And so you see the servers being recycled, the IP addresses may be being recycled, but they're also shifting locales or hosting facilities constantly. Okay. Part of this then ties into, if you like, the just-in-time provisioning. So the command and control servers can be hosted and set up asynchronously to the actual domain name registration. So I can set up the command and control server now and can be operating there and not doing anything until I actually set up the DNS, register the domain name that I'm interested in and point it to that particular device at that time. And of course I can deregister from the domain at any time as well. Okay. So the turnaround on these, depending on who you use as your domain registrar, may be about, I think the sweet spot seemed to be about 5 minutes. So the ability, so I can configure my command and control server, put it in somewhere, in some hosting facility, leave it there, it's all configured and all that. And the turnaround for making that command and control server live and answerable and discoverable by the malware, maybe as little as 5 minutes of me being able to log in, create and register a brand new domain name and get the free DNS that points to that particular domain name and set that IP address to my destination server. And of course the takedown and dismantling of that is just as fast. Some of the operators that we track, this turnaround of the registration and pointing to the server is about 15 minutes, and the window of time that they operate the command and control server actually answering the infected device is about 4 hours, and the dismantling and the actual physical removal of the server is 1 hour afterwards. So if you like, there's a 5 hours, 10 minutes, 5 hours, 15 minutes range where the servers are actually there, and where if law enforcement knew about them, we could actually do something about it. But it doesn't happen that way. So this is an approach that the bad guys have used, and there are so many advantages in the bad guys, so many advantages to the bad guys in actually using this type of technology and this approach. So is it all really good for the bad guys, or are there things that the good guys can do to sort of maybe counter it, or at least they'll be able to understand where the victims are? And so I was going to talk here a little bit about some of the techniques or approaches to DGA detection. So from a bad guy's perspective, what they really want is an algorithm or a system where these domain names are basically unpredictable. The more random they are, the better they are. However, as the bad guy, if they make them too random, then I can't guess where they are, and therefore I can't maintain control of my botnet that I've actually distributed there. So there needs to be an element that can be factored and calculated by the bad guys. What we see today are really a number of techniques. The most popular is the date and time. So using the current date timestamp, using that as the seed for the algorithm that's going through there. But the bad guys can use plenty of other things. So for example, one technique that was used was taking the 17th Google result for this day in history. Okay, so it's going to be fairly high up in the Google ranking. It's not really going to change, but it's only going to be visible on that particular day. So the bad guys don't even know what the domain, what the candidate domain names may be for that particular day until that day. Okay. However, their ability to register and set these things up, they're much more agile on that point. Another one was experimenting with really, what is the most shared news story on BBC News on a particular day as well. And given that it doesn't necessarily need to be a day, it just needs to be some particular epoch of time. Just a variable in this is how big the candidate space of domain names is for a particular day, and what the number of domain names that you're going to sample from that side. So if this is all going on, you mentioned that you have, say you're a large network and you've got maybe 50,000 devices on your network, and you've got a couple of hundred infected devices running malware that now have DGA command and control elements to this. You now have a couple of hundred devices there that are at certain times of the day are now cycling through lots and lots of domains and trying to do DNS lookups, discover whether or not there is an answer for that DNS response, a good response for that DNS lookup, and if there is an answer pointing to an IP address, then go to that IP address, make a connection, and transfer data. That entire process, there is a lot of, if you like, there's a lot of signal in that noise. So there's a lot of lookups. In particular, one of the interesting parts is the failed lookups. So if you look up a domain name that doesn't exist, you get an NX response, so no such domain name response. Traditionally, from a security perspective, especially a network security perspective, you don't normally look at this type of stuff. All the reject, all the stuff that the network doesn't like is noise, and you never really look at this. However, in this sense, when you're looking at DGAs, that noise is the signal for infections. So given that the majority of the lookups, domain names don't exist, and only a small handful of them will actually be real. And often what you'll find is that the malware, once it finds this real command and control server, it will stop doing the other routines of trying to locate the command and control server. So there's an abrupt change that goes on there. So one way of sort of visualizing what's going on here. So let's say I've got all these devices here that are infected, and they're constantly doing DNS lookups. They're either being used interactively by the humans there, or there are other software elements on there that are making connections and doing stuff. So from a DNS perspective, by monitoring the DNS, you're going to see all the correct domain resolution. So look up www.google.com and get a authoritative answer back, and here's the IP address. Look up xyz.blah.com, doesn't exist, and so you get a response from the recursive DNS server saying no such domain. Okay, NX response. So what I can do automatically is basically ignore all the successful ones. Okay, so I can just filter out all of that and only really look at the domain names that were resultant in an NX response. Okay, so this gives me for a period of time all of the rejected stuff that's happening on the network, all the domain names that just don't exist. What I can then do is effectively I can cluster these NX domains. So I can take all of these NX domain names that have appeared, and I can start grouping them based on various features and attributes. In particular, sort of if you like the statistical features, maybe a particular round. So given the size of the name, the frequency it was looked up, and other attributes there, I can group and cluster these automatically. Okay. What I can also then do is I have these clusters of just domain names. I've organized all these, if you like, in a mathematical process, and I have a group of domain names that were unsuccessful that are all roughly similar, the particular cluster. What I can then do, though, is I can look up which machines within the network actually looked up these, or clusters of these. Okay. So what I can do there is I can look for, if you like, another dimension of cluster. So I clustered on the features of the domain names. Now I can base it on clusters of who's actually looking these things up. Okay. So with no prior knowledge of any malware infection, but being able to use the DNS, I get a better feel for what's sort of going on in a particular network. Okay. Now I can do some feature reduction. So I can take some of these clusters and I can basically remove, even though these were non-such domains, many of them will be very similar to real domain names. They may just be misspellings or mashed keys or whatever, but they're statistically similar to existing known domain names or clusters of domain names. So I can automatically just throw those away. Okay. What I can also do is, if I've trained up a system and built up a classifier system, I can also delete, remove clusters of domain names of threats that I already know about. And what I'm left with then is a pool of clusters of domain names that are indicative of DGA behavior, and all the devices that are currently infected or are using these particular domain names. And so to give you an example, so here I've been able to remove everything else. I'm left with 2 distinct brand new clusters that I've never seen before based on the domain name structures. As a human, I'll start looking at these and I'll be able to say, well, actually, so these are all the failed attempts. There is a certain pattern to these. Okay, so at this stage, what we're looking at is the ability to detect devices that are currently infected, that have malware on there at a network level with no prior knowledge of what the malware could possibly be. Okay. And also, you're basically starting from knowing who all the infected devices are first. So if you like, from the traditional malware approach, has been you start with the malware, and you develop a signature, and then you find out who downloaded the files, and then guess who was actually a victim. This is the complete reverse. We start with the victims, and you work backwards to try to find out the piece of malware. So this morning I looked at my slide deck and I realized that I had about 20 slides that were full of math, so I simplified it. How many people in here, I don't know, have PhDs? Anyone? One? Okay. Anyone in computer science? A few? Okay, so I'll breeze through this. Okay, so I'm talking about NX domain clustering. So what this really means is that I can take, what happens in the clustering, I can take all this, this information, all these NX domains, and I can use techniques to cluster based on features. So when I look at things like statistical feature modeling, I can look at different groups of features. So for example, n-gram features. So I can look at given a particular domain name, I can look at the domain names that I've seen. So I can take a cluster of, say, 10 domain names that have all seem to be really similar. I can look at the frequency elements and distribution of character sets and the way that characters are organized, for example, and that gives me one set of features. I can take entropy-based features. So what's the change between all these different domain names? How similar are they? What's the distribution there? And I can take these structural domain features, such as what's the top-level domain names that they're registering. Is there a cycle to this? What's the length? What's the number, the frequency elements to these? So this gives me a number of features, and I can create a vector for this. Okay, so while my pictures before I showed you a nice little green circles with ticks and little circles, the red circles for the NX domains. What's happening there is basically a 2-dimensional model. Here, when I'm talking about the real domain clustering, you're talking about something like 40 or 50 dimensions. So it's a little bit harder to visualize there. The technique that we found to work very well is k-means clustering. So this is it's a distance measurement between different clustering techniques to be able to say how tight a cluster is. Now you can take these clusters. Another way of looking at it is clustering by party graphs. So that visualization, you can take so multiple victims will have partially overlapping NX domains. So we had this candidate base of domain names, but they're only tasting a small number of domain names. If I have enough infected devices, some of those tasted ones are going to appear by multiple devices. Okay, so I can graph that, and then I can actually start partitioning, using partitioning strategy for that to identify the vectors, and then I can actually do host associations there. So all of that really fits into the realm of machine learning, in particular unsupervised learning approaches. What you do with that is actually then build those, you can train and build new classifiers. So I can take a previously undiscovered threat, I can then understand this particular cluster, I can build a classifier for that cluster, and then I can now distribute that as a means of detecting and classifying this type of threat. So I'll skip past that. Well, actually, no. So, so there's 2 elements to the statistical clustering. So you can have the multi-class statistical clustering. And so that's going to help for you to label these NX domains, these clusters here, so it belongs to a particular threat. Another way is to use the hidden Markov model, HMM models, to come up with if you like, a loose signature that you would use to identify domain names that were successfully resolved. Okay, so here we have a DGA that is trying these different candidates, but hopefully some of them will actually work and actually go to live command and control servers. If I was just monitoring the NX domains, then I would never see the ones that were successfully resolved. So you need to use a different type of model to be able to detect the devices that are actually infected and which particular domain names were answering the command and control servers. Okay. So that gives you two inputs. So you end up with a model for automatically saying, based on network activity, saying that actually this device over here I now know to be infected and to be infected with this class of malware, as well as a way of saying, well, these are domain names that were successfully resolved, which may be candidates for real live command and control servers. Okay. So what about the botnet element of this? So understanding a real DGA-based botnet. If you're starting from this principle of monitoring the network traffic, at that point you've already identified all the victims. Okay. Now that's pretty good if you're an internal security team. You now know that you have 5,000 devices that are currently infected, and you've got a pretty good idea that this is not very good. You can start monitoring the network traffic, doing deep packet inspection, and see what data is actually being stolen or being traversed on your network. The problem is at that particular point, unless you're going to do forensics analysis on the particular host, you're not going to know what it's actually infected with or anything like that. And so you have to reverse the situation. And so one of the things that you have to look at is how do you go from knowing who the victims are and what the type of threat is to actually what is the piece of malware that's actually there. And so I was going to sort of step through an interesting one. So if you've gone through this process, you know all the infected assets, there are a number of things that you can do. So, how do you find the malware? So you start with a new DGA classifier on an NX domain cluster. You maybe create a regex, if it works, for describing the domain names. You then use that regex to look at all the successful resolutions. You end up with domain names that were successful, and hopefully these are candidates for live command and control servers. You can then, if you've got a big repository of all the malware in the world that's been running on your networks, you can then go searching through all the trace data from all those pieces of malware and look for those particular domain names. And then you can rank all those trace files and those pieces of malware based on what does the antivirus product think it is. Okay, and that will give you an answer, hopefully. There's a lot of assumptions there that you have trace data for all the malware, that you've seen the malware before, and that you can actually, it is actually detectable by antivirus products in the first place. Or you can, since you already know who the victims are, you go to one of the victim devices and do a forensics analysis and actually pull the malware sample from there. That is normally, used to be the case, used to be fairly good. However, the number of, shall we say, the more sophisticated spyware elements now tend to be more of a TSR or Java-based and things like this, so they're only operating in memory, and they make it considerably more difficult to do a forensics analysis on the actual host to find copies of the malware. So I'll give you one example. Malware v1. Malware has been known for 3 years, I guess, 2.5 years. Well, I was looking at one particular network. Using this particular technique, we sort of saw a number of devices that were infected. And if you like, these clusters generated about 1,900 domain names that were NX domains all clustered together over 3 days. Using the process that I outlined before, we're able to say that given that particular cluster and the structure of those domain names that were unsuccessful with this DGA, we then hunted for other domain names that were successfully looked up. Okay, and that resulted in 9 domain names that were active during that period, and effectively the bad guys had 3 command and control servers for each day, so they're just rotating through these. So very well organized, 3 domain names that were registered and using at the time, pointing to 2 IP address services, IP addresses that were hosting them. Probably too small to see, but effectively you end up with a very simple architecture of the domain names that were successfully resolving at that particular time, pointing into their command and control servers, all automatically enumerated. Okay. The interesting part is, so now I have the visibility of, I know the affected assets, I know what class of malware family it is probably based on the network structural features. I also basically know where the hosting environment is and a lot about, from previous history, who those hosters are and the types of threats that generally come from that particular area. But what about the other side? So I want to get that piece of malware and I want to understand more about that particular threat. In this particular example, I thought was interesting was that effectively the bad guys had screwed up their whois information. So yes, they were using fake data to register the domain names, but they're using the same-ish fake data across multiple registrations. More importantly, as part of their campaign, so they had their command and control servers using the DGAs and how they registered those particular domain names for the DGAs. They actually reused some of those credentials for their distribution, so their drive-by download parts. And so what we found is that tracing back from those domain names and the whois registrations, we found their other exploit packs. So they were running Black Hole on their drive-by download sites, and also one was running the Sakura kit. And you sort of see, their structure for their drive-by download domain name became a feature for identifying other drive-by campaigns that they were running at that time. So what we found that the threat was related to the Better Business Bureau and the Nature spamming campaigns. So the Malware distribution that they were using was focused on much on the spam side. Since all the exploit sites were live, we were basically able to milk those sites. So while those sites were still live, just keep on pinging them and getting copies of every single piece of malware that they were generating. Okay. Interesting enough, what they were doing was that they were also generating, for every single successful exploit, they generated a new piece of malware for everyone. So every single piece of malware for every infected device had a unique hash value for that piece of malware. So they're creating it on the fly. Okay. I think one of the interesting parts, though, was that Malware had been discovered 2.5 years before this time. However, and people had analyzed it many, many times and understood how to decrypt the command and control configuration files, how to decrypt the traffic. They also had done a lot of work into the peer-to-peer elements. However, the DGA elements had remained completely missing from the analysis because they were heavily disguised, but they're also a fallback condition. And so, the DGA element provided this guarantee that the malware would successfully keep on running. So what that means today, though, is that Malware 1 is still out there. All those infected devices are still out there. And while the command and control channels that were in the configuration files have all been taken down, and most of that botnet operators' command and control infrastructure has been removed, the peer-to-peer network has been taken over and is no longer useful to them. The DGA is still running on all those machines. The bad guys still know what the DGA algorithm is, and so at any point in time, they can now go register a new DGA domain name and take over this network at any point in time. Okay. So if all these things, we start off from what the bad guys are doing, what the good guys are doing, and meeting in between of how they messed up in one particular case, what about for the bad guy I want to build a better DGA going on? Now, there are only a number of things that you can really do for the DGAs. Okay, so the scope of the DGA is critical. Okay, so if I have too many daily domains, then as the bad guy, if my algorithm has too many daily domain names, then as from the algorithm side, then I'm only really sampling the number of victims. Okay, so I may have a botnet of 1 million hosts out there, however I'm only sampling, let's say, 1 in 10, so I can only control or issue commands to 1/10 of my particular botnet. If I have too small, if that space in potential domain names is too small, then the probability that I'm going to be blocked and filtered is much higher. And if I recycle my domain so there's not enough entropy in my algorithm, then I will have collisions, and it'll be easy for good guys to detect which particular domain names should be blocked and have a high success rate. Or there should be a paper coming out probably next week from Dambala. Will show when the bad guys do get their algorithm slightly wrong and their collisions are a little bit too high, you can basically hijack their entire network based on the collisions of the domain names that they didn't realize, but the host was still cycling through these domain names, and we're able to register them faster than the bad guys could and take over their networks. So if you like, there's a sweet spot, and that sweet spot will change over time. So there are dynamics in the internet hosting where the physical location of these servers are, and the way that the routing is being configured, and the way the hosting facilities break up and whatever. There is also changes in the blacklist and the capabilities of the blacklist technologies and how frequently they're updated, either by IP or domain names. You have the changes in the distribution technique with the drive-by downloads, or whether there's worming techniques, or there are other elements there. And frankly, one of the biggest causes of concern for the bad guys is if a particular sample is intercepted and they're reverse engineered by the good guys and signatures start going out. So there's a lot of, things that come into play for the algorithm. So what we found was that that noise, the stuff that you normally just forget about, the failures, the NX domains, are actually the tool that's you can use to detect the infected devices independent of the malware, which is cool. But so from a bad guy's perspective, if the good guys are monitoring the NX domains, what can I really do about this? And I think that so one way is to alter the algorithm so that very few NX domains are registered. So I talked about clustering technology. So for a cluster technology to work, there has to be a minimum threshold for filling up a bucket for a cluster. So if my algorithm is slow enough and the number of NX domains that I generate is less than that particular threshold, I can always avoid this type of clustering technique. I can use algorithms that randomize everything. So I talked about features about the structure of the domain name. Now if I randomize everything, then that's very good. But on the practical side, from the bad guy, if I randomize everything, then it's going to be almost impossible for me to sample and take control of those devices. I can use an algorithm that creates domain names that look like popular domain names. So I talked about removing false positives from the clustering techniques by looking at real domain names or popular domain names and removing effectively clusters that would be fat-fingered type domain names. So if they can make them look close enough, maybe they're much more difficult. They could also employ a different DGA for every single infected device. So use either the same algorithm in a different seed, wouldn't make much of a difference. However, if I use a different algorithm for every infected device, then that would make it almost impossible for the DGA detection type system to work. However, it would also make it pretty much impossible for the bad guys to control entire botnets. They can only control individual devices at a time. So is it possible to do away with the NX domains entirely? So some alternatives to DGA structures do exist. We've seen some malware use domain wildcarding. So they have a static 2LD or 3LD that may be legitimate. So we see some malware use free dynamic DNS providers. So for example, you see co.cc is a free DNS service, and you can register any third-level domain on there, and you see the bad guys using a DGA to try these third-level domains, for example. You can also just use it at the server side. So remove all of the code from the client, do it at the server, and use the server to create new domains for every new piece of malware itself. Such that the malware has a command and control domain name. However, it's always going to be the live command and control server. In reality, though, it's not really practical, so that means that the malware would have to be updated every single time, constantly, so you'd be able to probably detect that you have a device that's pulling down lots of files and installing files continuously normally from pretty bad reputation sites. So wrapping up on the conclusion side, what can we sort of look at this? So first and foremost, it really is that the DGA usage in malware is on the rise. In fact, the majority of the malware that we actually see today used by the largest criminal operators, so for example, the TDL group that we currently track has an estimated about 25 million devices under their control. They sublease, so often what you'll find is that a device that has TDL3 or TDL4 on there, so it's a rootkit, an MBR rootkits there. They basically sublease their infected devices, and so you often find that the device will be compromised, will have the TDL rootkit on there, and then it will have maybe 3, 5, 8 new pieces of malware actually running on there as well in sublease. And so it's become popular, it's become a fallback technology, and because it's been integrated into the Zeus and SpyEye and even Poison Ivy and some of the other kits, it's just there. It's a tick box that you add to your malware construction side. Okay. The bad guys are also trialing different algorithms, and some work, some don't. There's still, if you like, there's a sweet spot that still needs to be explored. So the sweet spot for DGA algorithms is still experimental. They're designed. The whole point of DGAs has been used to provide the resilience against takedowns and blocking technologies. And so as those technologies alter, there's a Goldilocks zone for the DGA optimization. We also see that the NX domain monitoring is actually a key and critical feature in actually detecting these types of threats. In fact, from the DGA-based way, it's the only real practical way of detecting this type of activity from a fallback side. However, there's some limitations to this approach. This is an approach that you can detect all the infected devices, and you can arrive at a pretty strong conclusion that they are infected. You just have no idea what they're actually infected with. Okay, and then you have to do other work to find out what data is actually leaking from those things. However, you can use these learning systems to automatically identify new clusters, identify entirely new threats, and track them in real time. So that's led to a number of new automated detection technologies, both in commercial space but also in academic space. So I talked about some of the new clustering techniques and clustering approaches. I think when you look at some of the universities that are now focusing, that started from computer science and then have developed computer security courses. When you look at their PhD programs now, a lot of new research is going into cutting edge clustering machine learning technologies, but applied specifically to security. And from what I've been able to observe, these types of approaches have been A, very successful, but B, have been able to detect many of the threats that at a network level that have just not been visible before, mainly because of the volume of the data. So in the past we used to talk about if you want to monitor the network traffic, I'd try to do deep packet inspection on a per stream basis. I'd be very selective about what I wanted to do there. I'd also make use of net flow to get the overall statistics because the volume is too high. Now, though, with these types of classifier systems and machine learning types of approaches, I can shrink that type of visibility and what I actually want to detect down to a few hundred K. I can run that in memory, and I can stream and I can watch all streaming data simultaneously. So, for example, one of these types of techniques is already in operation and has visibility of about aggregate of about 3 terabit per second of DNS traffic from around the world. And still be able to detect all the devices that are actually infected. Okay. I think that there's a whole new research area that is coming up that still is unsolved territory. And so I'm working with a lot of the universities and master's programs and things like that, try to solve small pieces of this. So let's say that using this type of NX domain classification system, you're able to detect these thousands of assets, devices are currently under control, and you've got all the network aspects to it. Great. Now, how do I figure out what the piece of malware is? Especially with some of the TSR type pieces of malware. How do I make that leap from network activity, saying it's bad, to what is this threat that's actually there? Now, what we've seen is that using these types of techniques at the network levels, they are on average about 150 to 160 days ahead of the malware actually being uncovered. Okay. And so there's this delta for, okay, if I know when there's infected assets around there, how do I clean them up? And traditionally, for me to figure out how to clean them up, then I need to know what the piece of malware is so I can write a cleanup script. And so there's a gap in security technology and incident response that still needs to be closed. And I suppose the last thing really is about the DGA approach is highly successful. Now, in chat sessions with the actual authors of many of these malware kits, they are extending their DGA capabilities. They're developing better algorithms, but better back-end operational techniques for managing their command and control servers and regaining these types of regaining control of these particular botnets. And so, evasion. So the evasion techniques in this particular area are quite sparse, but they don't really need. So the bad guys using DGAs, there is a very narrow window where they can operate in successfully. However, if they operate in that particular window, it's practically impossible for the traditional defenses to operate. Not just the traditional defenses, but also from the traditional approach to removing and shutting down the threats. So both of tracking who the authors are, being able to take down the command and control servers, or the traditional approach has been to hijack the domain and point them to sinkholes. With DGA-based malware, that is not really possible. The only exception being DGAs that have high collision rates, and where the good guys can go out and register the domain names faster than the bad guys can, and then they can sample the part of the botnet today. And look at that. Any questions? I removed all the formulas. Sure, question. I think they've got a microphone just coming up.
You were talking earlier about the k-means clustering, and I'm guessing one of your features would be age of the domain, and that would be relatively constant. I mean, there's a window in which these domains are deployed very quickly, and
as it happens, the domain registration age is not used. So we're taking only the network attributes that are visible on the network. So the domain age isn't going to be visible because it'll be contained in the domain registrant details, so who is details. There is maybe a way of getting around that, and that would be using a passive DNS system to say when was the first time it was ever seen, not necessarily when it was registered. These techniques have been predominantly on the passive side only, so only observing the network traffic. Mainly because it was easier to do asynchronously from a research perspective, but also to leave less of a fingerprint behind for the bad guys to actually detect what's going on. Cool. Any other questions? In that case, thank you very much.